Welcome back to another lesson on implicit functions. Last time we were able to transform an implicitly defined function for a rotated ellipse into the expression seen at the bottom of the screen. Notice y is on the left-hand side and all the x's are on the right-hand side. They are completely separated from each other. This is easy to graph. Plug in one value for x and one unique value spits out for y. Alas, it is not always so simple. Sometimes we get a function like this. Go ahead and try to separate the x's on one side and the y's on the other. There doesn't seem to be an easy way to do that. So how do we graph a function like this? Well, we could pick an x value and then keep guessing y until the function f of x and y is equal to 0. So here x equals 0.2. My first guess is y equals 0. Plugging those two values into f gives me 0.199840, underlined in red. This is not 0, so I must guess again for y. Repeating that process systematically gives me these results. Every time f changes sign from positive to negative, I go back and add another decimal to my guess for y. Y equals 0.423 gives me f equals 0 up to 4 digits. I could keep following this pattern to get more and more digits. So the old guess and check is one approach, but it gets tiresome, especially when you have to do it for each and every one of the points on the graph. Is there another way to find x and y pairs that make the implicit function f equal to 0? Let us start off by setting y equal to some constant k. Now we are left with a function of only one variable instead of two. This is a good start. Consider k equals 0.4. The function f of x looks something like this. Notice there are two roots, seen in red. This is where f of x crosses the horizontal axis. How do we find roots of a complicated function? We can use root finding algorithms like Newton's method seen here. This is a fairly common approach covered in many standard textbooks, as well as previous lessons I have made on this channel. It works very well in many cases. However, there is one major drawback. The derivative f prime of x, boxed in dark red, is a function of x. Sometimes the derivative of a function may be laborious to find. Other times, we might not even be provided f as a function. That is the case when looking at a table of discrete data points, for example. In such a situation, it is simply not possible to find f prime of x. However, we can approximate that by a linear slope m. That is effectively the secant method. The secant method was also covered in previous lessons, but here I've repeated it for easy reference. Don't get lost in all the notation just yet. We will visually see what all this means. To do that, we are going to focus our attention on the rightmost root in this graph. We will zoom in on the orange box. Take the function value on the left at x equals 0.8 and the right at x equals 1.2. Now extend a line between those green dots. Algebraically, it is quite easy to find the intersection of a line with the horizontal axis. That red dot looks to be about x equals 0.93. The true intersection of the curve, seen by the blue dot, is just a little bit more than x equals 1.00. In the table, notice that the y column remains constant at 0.4. Meanwhile, the x values change. We see the vertical coordinates of the left and right dots boxed in green. Those give us a slope m in the last column. Following the secant method equations shown earlier, the first iteration gives us 0.935, boxed in red. I'd say that's pretty close to what the graph showed us. Then we just keep repeating that pattern for every other row in the table. Go ahead and try this for yourself. See if your numbers match mine. Notice by the 9th row that x has converged to 1.005, as boxed in blue. Every digit in the 8th row immediately above it is identical. In the next column over, we see entirely zeros. Lastly, the m column has given us a divide by zero error. These three things are telltale signs that we have maxed out the number of digits this software can handle. Our answer has converged on 1.005 when y equals 0.4. These two coordinates make the implicit function f of x and y equal 0. So notice that for y equals 0.4, there are two red dots. I just showed you how to find the one on the right. The one on the left can be found in a similar fashion. You just have to use different x0 and x1 as starting points in the secant method. This would also be good practice for you to try on your own. Basically, we can do that for other values of y, 0.2, 0, negative 0.2, negative 0.4, all the way down to negative 1. If we go beyond that, our function will have no roots, no intersections to find. These pairs are seen connected by horizontal red lines. This gives us a pretty good picture, except on the top of the blue branch. How do we fill in that gap? One way is to apply the same approach, except make the variable x equal to a constant k this time. That leaves us with a function of y only. We have reduced a function of two variables down to a function of one independent variable. Much easier to handle. Select x equals 0.6. A plot of f of y looks like this. There appear to be two roots for this choice of x. The curve crosses the horizontal axis around negative 0.75 on the left and around 0.6 on the right. We will use the secant method once again. Exactly the same, except I replaced x by y. This time x is a fixed number and y is our unknown quantity. We want to find y. Once again, we will focus on the rightmost root. Use starting values x equals 0 and x equals 1. The green line crosses the horizontal axis around x equals 0.39. That is in red. The actual function crosses at 0.59. That is shown by a blue dot. This table should look very similar to the previous one. Notice that x is now a constant at 0.6. Y is the variable that changes. Boxed in red, I'd say 0.391 is very close to our guess from the graph. Use the equations for the secant method for every other row in the table. By the 10th row, we have converged on y equals 0.59. That is boxed in blue. Once more, I encourage you to make this table for yourself and compare your numbers to mine. Then use a different y0 and y1 to find the left root. Those two roots are plotted here in red. Y equals 0.59 goes on the upper branch of the function, blue curve, and y equals negative 0.74 goes on the lower branch, orange curve. Both of those are connected by the vertical line, x equals 0.6. Again, we take cross-sectional slices, x equals 0, then x equals 0.2, 0.4, 0.6, all the way up to 1.2. Each pair of roots is connected by a vertical red line. This does pretty well until the rightmost portion of the graph. There is a rather large gap between data points over there. How can that be resolved? One way is to combine the horizontal slices and vertical slices together. That way they can compensate for each other's weaknesses. That gives us a pretty complete graph now. Another way is to abandon the restriction of uniform slices. Those exceptions are boxed in red. Every other slice is 0.1 units wide. By the way, the data on the left corresponds to the blue upper branch, and the data on the right corresponds to the orange lower branch. Go ahead and plug each x and y pair into the implicit function shown at the beginning. F of x and y should equal 0 for each pair. For example, I have selected x equals 0.3 and y equals 0.499315 from the table just seen. Plug them into the implicit function and evaluate. Make sure your calculator is in radians when you evaluate cosine. The answer boxed in red is equal to 0, within rounding. At least check a couple other xy pairs from the table to make sure f of xy equals 0. It's your choice how you want to space your data points to get a complete graph. In that sense, this might be considered more art than science. One way or another, once you have a reasonable number of data points, you can interpolate between them to plot one smooth curve, like the one seen here. This represents one closed loop of the implicitly defined function. But wait a minute, if we extend the domain of f of x, notice the oscillations. There appear to be an infinite number of roots. That means there must be an infinite number of loops like the one we just saw on the last slide, and they extend horizontally along the x-axis. You'd have to follow a similar procedure to plot each of those other loops point by point. What about f of y? This function appears to be more dominated by the parabola. Only the two intersections we already found, and no more. That means there are no more loops above or below the one we just plotted. This is an art and requires hands-on practice to fully understand. Plug this data for x and y into the original implicitly defined function. Convince yourself that f of x and y equals 0 at each of these points. If you're feeling really audacious, find each of these roots yourself. Apply the secant method to f of y for each vertical slice, x equals k. Do your numbers match mine? Let us know in the comments section below. Also, feel free to ask questions and give me feedback. I appreciate your support and hope to enhance your understanding and appreciation of mathematics. Thanks for watching. See you next time.